So this process can be kind of analogous to manufacturing, where you have a certain set of components that goes together to make a finished product. So you can see this resembles a chemical equation in some ways. So to build a bike, you need one frame, one seat, two pedals, one handlebar, two tires. That equals one bike.
All right, and let's say we have the following parts. We have 63 frames, 88 tires, 73 seats, 92 pedals, and 56 handlebars. So we need to figure out how many bikes can be built and which one of these parts are going to be our limiting factor.
Okay, so the approach to this is you would take each of the available parts and divide it by the number needed per bike, and that'll tell you how many bikes you can get out of that.
Yeah, so with 63 frames, we only need one frame per bike, so we know that we can build 63 bikes.
So 63 frames, 63 bikes.
And then we have 88 tires, but if we look up, it takes 2 tires per bike. So we take 88 divided by the coefficient in the reaction, and that gives us the total number of bikes available for us. It would be 44 bikes.
Yeah, I'm not even going to write this. So I'm going to say we get 63 out of that. We can get 44 bikes out of that. So right now, 44 would be our limiting number. But let's continue on.
73 seats, but since there's one seat per bike, we can make 73 with that. We have 92 pedals. 92 divided by 2 is what? 46. 46 bikes for that. And then we have 56 handlebars. And then we can make one for one, so that's 56. So we know tires are going to prevent us from building more bikes, so that's our limiting reactant. And we can only build 44 bikes. So
unless you want to build them without tires.
And then you'd run out of pedals after a while and just wind up with some seats.
So it's the same idea in a chemical process then. We're going to need to, but the difference is usually your input is in grams of the substance, and we're going to have to take it to moles, so that we can actually compare particles to particles and then know which one is going to limit us. Let's take it to a chemistry example now.
All right, so here we have a limiting reactant and excess reactant defined. The limiting reactant is the reactant that runs out in a chemical change. Determines the amount of product that is formed, because once you run out of one chemical, you're done. You're not
just like in the example we ran out of tires. That's it. You can't construct any more completed bicycles.
And then, of course, if the limiting reagent is the one that runs out first, the excess reagent is what's ever left over that's not consumed, which would be considered waste if you are in manufacturing or in industry. You don't want to have a lot of excess reactant wasted each time.
And you hear us using two words there. Mr. Hunter just used it. The word reagent is the same as reactant in this. So limiting reagent is one and the same thing as a limiting reactant, so don't let that throw you off, because we've heard it both ways, Mr. Hunter and I, so we'll probably use them interchangeably.
All right.
Let's hit an example problem now. So here's a typical limiting reactant problem. You have 34 grams of ammonia reacting with 36.5 grams of hydrochloric acid to form ammonium chloride. That would, of course, be a synthesis reaction, and you're asked to determine the limiting reactant. So I want you to pay attention to the strategy, because we're going to show you this strategy, and then we're going to show you an alternate strategy.
And also write it down, of course.
So, like most stoichiometry, just about all stoichiometry, you got to begin by writing the balanced equation.
So knowing how to name, once again, comes in handy.
So, which we've done right here. So NH3 is ammonia, hydrochloric acid, this is ammonium chloride, and it's balanced, they're all ones, and the coefficients are all ones. Okay, so the first job after getting the balanced equation is then start with the given amount and determine how many moles you have of each reactant, which we can do this with the official symbol is N is your number of moles, which we haven't done. We usually just put like question mark moles, but this is kind of the more proper way to do it. So this is your number of moles of ammonia, and I've got that all set up here, except I didn't put the molar mass in. And this is the number of moles of hydrogen chloride, and I've got 17. That all set up.
So it's 17 for ammonia. Nitrogen is 14. Each hydrogen is 1.
17 grams, and this would be what? 36.45. We'll just say 36.
36.46 if you want.
36 point. All right, we'll take it to the hundreds. 36.46 grams.
So 34 divided by 17 is, well, 2.
so we have 2 moles of NH3
And
because
1
the
mole,
grams divided out, and we have
1.00.
1.00 moles of HCl.
So in this reaction, I would say hydrochloric acid is our limiting reactant.
Limiting reactant, and this is the excess reactant, ammonia. We're going to have leftover ammonia when all the hydrogen chloride's used up.
So remember, it's not just what do we get here, right here. You also have to take the coefficients of these and divide it by them. But since they're both 1, it's going to be 2 moles. So let's say we had 2 HCl up here. Instead, that'd be 1 divided by 2 equals a half. That would still make it the limiting reactant. But you can't forget to put your coefficients.
So you're supposed to divide, and you're right. I kind of jumped ahead there. You would divide that by the coefficient, and like Mr. Hunter said, they're all 1s here.
You can write it in.
So we can divide by 1.
Divide by 1.
Which kind of levels the playing field then. If you think of the coefficients out here would represent, like in the recipe, how many cups of that thing or how many units of that thing you would need. So we need to divide by the number of units. If the coefficient's higher, we need a correspondingly larger number of moles of that thing to go forward. So dividing by 1 in this case is still 2 is still going to be bigger than 1, and so the hydrogen chloride is the limiting reactant. So we're going to go on to another example and show you kind of an alternate approach to a limiting reactant problem.
So here is example 2, 190 grams of titanium 4-chloride reacts with 72 grams of water, producing titanium 4 oxide and hydrochloric acid. So in this case, they want to know what is the limiting reactant. So again, the procedure for this is to write a balanced chemical equation. There it is. 1 titanium 4-chloride plus 2 moles of water yields 1 mole of titanium 4 oxide plus 4 moles of hydrochloric acid.
Okay, so the next job, we need to determine how many moles of a product can be formed from each given amount. So we've written the given amounts here, okay, and you just pick one of the products. I chose titanium 4 oxide. So we're going to basically see from these starting amounts how many grams of that product can we get.
All right, so then we convert each of these to moles. And you can see there's a long, drawn-out process. So first is titanium 4-chloride. So you take the given, which is 190. You convert it to moles of titanium 4-chloride. And then you have to take moles of titanium 4-chloride to moles of titanium 4 oxide. And that'll give us an answer of, let me find out, 190.
So we've got the answer calculated. It's 1.00 moles of TiO2. So let's go on to and look at our second amount of reactant. So now we're going to, again, change moles of water into moles of titanium 4 oxide. Okay, the grams, oops, dang it, pencil. Grams of water, divide out. Moles of water, divide out. Now notice our mole ratio is different here because the coefficient of water is a 2, titanium 4 oxide is a 1. Okay, so we're going to end up dividing that by 2. And Mr. Hunter, what did you work out there, sir?
Basically rounds up to 2.00.
2.00 moles of TiO2.
So again, now we know that titanium 4-chloride is going to be our limiting reactant.
Yeah, so this one, the lowest result, we're only going to get a mole of titanium 4 oxide. This is the limiting reactant.
Yeah.
Okay, now once you've identified that, that's important because that's going to limit the process. That's going to be the starting point for any subsequent calculation. So keep that 190 grams in mind because we're going to show you some typical follow-up questions that you might get asked in a limiting reactant problem. Once you find the limiting reactant, then a lot of times you have to use it to do something else.
All right, let's look at a going further question then.
So a couple of extension questions that can be asked, and you can see at the top we've just transferred the equation over onto this slide, same equation we had last time. There was the starting amounts that were given. We know that titanium 4-chloride is the limiting reactant. So question 1, in that reaction, calculate the mass of the titanium 4 oxide product. So this is an example where we have to use this limiting quantity because that's going to drive the reaction. So if we want to know the mass of TiO2, we could start from the mass of titanium 4 chloride, but since we've already worked it out to moles, let's start from the 1.0 moles of TiCl4, because we already had that worked out previously. So we need to transfer 2 moles of titanium 4 oxide, 1 mole TiCl4 is 1 mole TiO2. And now it just becomes a mass or mole to mass conversion. So for a mole of TiO2, how many grams do we have?
79.8.
79.88 grams. And moles of titanium 4 oxide divide out, moles of titanium 4 chloride divide out, and we're left with grams of titanium 4 oxide.
Equals out to be, with sig figs, 80 decimal point grams.
80 decimal point grams TiO2. So that's the most you're going to get out of that reaction, even though you have lots of extra water. You ran out of titanium 4 chloride, so that's it. And now another problem that you get asked very often is, what is the mass of the leftover excess reactant?
Yeah.
So in this case, how do we approach this, Mr. Hunter?
Well, first we have to know how much limiting reactant we had, which we knew we had 1 mole of the limiting reactant. So for every 1 mole of TiCl4, we're going to have 2 moles of H2O consumed. So we have to figure out what 2 moles of H2O weighs and subtract
Yeah, you're basically
going
to convert this amount into moles
water
of that are going to be used up, and then go. So we want to know the mass of H2O consumed. So we're going to say 1.0 moles of TiCl4, and we're going to switch it to moles of water. So 1 mole TiCl4 is 2 moles of water.
Just have to find the mass while we're at it.
And now we're going to find the mass while we're doing it. So for a mole of water,
it's
18.02 grams of water. And the moles divide out there, the moles of that divide out there. So we come out in grams of water.
It should be 36
grams of water. So of course that is not the answer.
We now have to take.
Actually, it is the answer.
Well, it's the
but
answer.
It's not the answer for the reason you think it's the answer.
So then we have to figure out lastly how many grams of water are left over. So we take the initial amount of water, which is 72, subtract 36 from it, and well, we get 36 grams left over.
Just so happened that it worked out that way, but you have to subtract to find the answer.
Yeah.
So we'd have 36 grams, half the water would be left over unreacted.
All right, have a good night.
So we'll be practicing this a lot more. It's an important concept. See you soon. Okay, so here's your limiting reactant post-video question. We have an unbalanced chemical equation here, so make sure you balance it. And then we have some given information. We have 4 moles of iron 3 chloride, that's this reactant, reacting with 4 moles of oxygen gas. Remember, these are not the coefficients, these are the amounts that were mixed together for this reaction. So your first task is going to be determine the limiting reactant. Which one of these is going to be used up? Will the 4 moles of iron 3 chloride get used up, or will it be the 4 moles of oxygen gas? Second question, how many moles of chlorine can be produced in this reaction? And of course the limiting reactant is going to tell us what's the maximum amount of product that we can get. So balance the equation and then try your hand at these 2 questions and be ready to discuss it when we meet again.